In this video, we will look at section 2 of our polynomial interpolation chapter. So in particular, we will focus on Newton interpolating polynomials. In the introduction section, we saw that the coefficients of the interpolating polynomial can be found by inverting the matrix using the following equation. This matrix can often be ill-conditioned and difficult to find an inverse for. Alternatively, a simpler method can be used to find the interpolating polynomials using Newton's interpolating polynomial formula. So given n plus 1 data points of the form xi, yi, where I goes from 1 to n plus 1, a polynomial of degree n passing through these points is given by the expression shown here. Now the unknown coefficients in this expression are the bi's, the b1, b2, b3, etc. The coefficients bi are defined recursively using the divided differences as follows. So b1 is equal to y1, b2 is equal to the divided differences of y1 and y2. So we use these square brackets to denote the divided differences in this context. And this definition is that y2 minus y1 divided by x2 minus x1. Now b3 is the divided differences of y1, y2, y3, which is defined recursively as shown here. So this y1, y2, y3 is defined as y2, y3 minus y1, y2 divided by x3 minus x1. And we know from here how these are defined. So this is y3 minus y2 divided by x3 minus x2, that's this one here, minus y2 minus y1 divided by x2 minus x1, that's this one here. And then all of that divided by x3 minus x1, which were the ends of our interval here. And this continues up to bn plus 1, which is defined as the divided differences shown here, which again is found recursively using this, these definitions. So we can illustrate this in a table. So for x1 up to x4 and y1 up to y4, b1 is equal to y1. And then to find b2, it's y1, y2. So we follow these into the next cell of our table. So y2 minus y1 over x2 minus x1. And then here we do the same thing. So we combine y2 and y3, and here we combine y3 and y4 using the expression for the divided differences. b3 is then y1, y2, y3, which can be found by combining these here. So y2, y3 minus y1, y2. So the y2, y3 comes from here, and the y1, y2 comes from here. Again, in the bottom part of our table, we do the same thing. So now we want to define y2, y3, y4. So the y3, y4 comes from here, and the y2, y3 comes from here. And then these two can come together to find b4, which is y1, y2, y3, y4, which comes from y2, y3, y4, again comes from here. y1, y2, y3 comes from here, and we can see kind of what those were defined as we go back up the table. So to program this, we have to use a recursive function. So let's look at an example. Let's use Newton's interpolating polynomials to define the interpolating polynomial to this data. So we've just got 2 points here, 1, 1, and 2, 5. So we want to find this interpolating polynomial that passes directly or exactly through these 2 points. So we have 2 data points, so we will create a polynomial of the first degree. So that means we need to find the coefficients. So b1 is equal to y1, which is 1. b2 is equal to this divided differences, y2 minus y1 divided by x2 minus x1, which is equal to 4. So the interpolating polynomial is shown here. So this was b1 plus b2 times x minus x1. which is equal to 4x minus 3 when we expand it out. Okay, let's look at another example, add an extra data point, and again, using Newton's interpolating polynomials, find the interpolating polynomial to this data. So this is the polynomial, the plot that we are looking for. So here we have 3 data points, so we create a polynomial of the second degree, and we go ahead and calculate our coefficients. So b1 again is equal to 1, b2 again is equal to 4, so our first 2 data points were the same, which means our b1 and our b2 are the same. And then we've added a third data point. So we calculate our b3 using this recursive formula, and we find that b3 is equal to negative 3.5. So the interpolating polynomial has the form shown here. So again, this is our b1, b2, and b3, which we can expand out and get the expression for the polynomial shown here. Again, we can add another data point. So these data points are all the same as the previous example. We're just adding on another one. So we've got 4 points, so we're looking for a cubic function. And we can use the this table to illustrate how we achieved each of the coefficients. So this is b1, b2, b3, and b4. So the interpolating polynomial has the form shown here. So again, this is our b1, b2, b3, and b4. And we can expand this out and get the expression shown here. Again, let's add another data point. So again, using Newton's interpolating polynomials, we want to find the interpolating polynomial to this data. So adding on another point here. So we're looking for the polynomial of the form shown here. So we have 5 data points, so we will create a polynomial of the 4th degree. And again, we can put together our Newton's interpolating polynomial table as shown here. So this gives us our b1, b2, b3, b4, and b5, and allows us to construct the interpolating polynomial of the form shown here, which we can expand to get the expression here. So what's important to note with all of these examples is when we expand the polynomial out in this form, it's exactly the same as what we would have gotten if we solved the system of equations to find our coefficients a0, a1, etc. And you can also verify that using the polyfit function in MATLAB. So the important thing with the interpolating polynomials is that they are unique. So the different methods that we use to construct them should all result in exactly the same polynomial. So Newton's formula for generating and interpolating polynomial adopts a form similar to that of Taylor's polynomial, as you may have noticed, but it is based on finite differences rather than the function derivatives. So the coefficients of bi are calculated using finite differences. One advantage of this form is that the degree of a Newton's interpolating polynomial can be increased or decreased automatically by adding or removing more terms corresponding to new points without discarding existing terms. So you probably noticed as we were going through the examples that we were just adding on an extra point, and we didn't need to recalculate all of the coefficients bi that we already knew, because those did not actually change as we added new points to our problem.